Okay, hi everyone again. Hope you're all doing well. So, last time on Tuesday, we obviously talked about Grover search and how it can be applied to a really quite large class of classical algorithms, but it only gives them a quadratic speed up, unlike something like Shor's algorithm, which gives a exponential speed up. So it's a lot more powerful. So that is actually going to be the end of sort of the section of the course on quantum algorithms, because there really are only two quantum algorithms that matter. Just Shor's algorithm / phase estimation and Grover search, and the few baby ones that we did at the beginning. So today we're going to sort of move on to the more information-y section of the course, the real quantum information section of the course, rather than sort of quantum computing stuff. And in particular, we're going to introduce the idea of a mixed state, which roughly means combining quantum mechanics and classical sort of probability theory together into one sort of merged description of a state. It turns out this works rather more nicely than you might think. So yeah, there's sort of really, you might think this is just a sort of hack that you use every once in a while when you need to talk about classical probabilities and quantum mechanics at the same time, but actually it's really, the way you want to think about quantum states most of the time uses this formalism that can cope with classical probabilities, and we'll see why this lecture. So suppose we have some quantum state, but for whatever reason we don't know exactly what that state is. Okay. So if it was a classical state, we sort of know the formalism we would need to use to describe our knowledge about it, which is we'd describe it using some probability distribution. That describes how likely we think each possible state is. Right? It's encoding our beliefs about the state of the system. Okay, so this is sometimes called Bayesian attitude to probability. We're thinking about probability in a more general framework than just you have a large set you have a large set of repeated experiments, and you want to look at the distribution each one. We're willing to use probability to just describe our beliefs about a single state when we don't know what that is. And in quantum mechanics, we can just do exactly the same thing. In particular, we can describe some state by what's often called an ensemble. It suggests a collection of states, but really it can just be used to describe belief about a state, which is just a set of state probabilities, pi, together with some state psi I, right? So this is just saying that we think there's probability p0 of the state being psi 0, p1 of the state being p1, and so on. So these are probabilities, which just means that they're all positive numbers, and we have a sum over pi is equal to 1. And these psi i's are literally just normalized quantum states. So in particular, we have the inner product with psi I with itself is equal to 1. Okay, not going to assume that they're orthogonal quantum states. Could maybe have, 50% chance of being the 0 state, 50% chance of being the plus state, whatever we like. And so this is, this ensemble of states we would call a mixed state. Okay. So now we can imagine we have the state where we don't know what it is, but we know the probability distribution for what it is. And we can do some measurement of the state. And recall that a measurement is just described by a set of possible measurement outcomes M, each of which has an associated projector, right? So for example, a measurement of a qubit on a computational basis, we have one possible outcome, which is 0, with a projector that's just a projector onto the 0 state. And similarly, there's outcome 1 with a projector that's a projector onto the 1 state. Okay. And the rule for a pure state, for an ordinary quantum state, it's just that the probability of getting M is psi PM psi. But in this case, we don't know what the quantum state is. So we want to know the sort of average probability of PM over all the states. How do we do that? Well, we know how to deal with we know how the rules for dealing with conditional probabilities, right? So all we do is we sum over all the possible states, I, and then we have PI, and then we multiply it by the probability of getting M conditioned on the state being psi I. Okay? So P of M conditioned on I, we can just apply the ordinary rules, the ordinary measurement postulate for how to deal with probabilities of getting different measurement outcomes, and it just says it's psi I, projector into the state M, psi I. Okay. Now, here's the slightly clever bit. We can do the following trick. Seems sort of arbitrary and unnecessary, but we can just introduce just an identity function into this inner product. So I'm just going to call this, I'm going to expand this identity function into an orthonormal basis set of projectors or orthonormal basis J. Okay, so it's just exactly the same formula as before. I've just added in this unnecessary sum over J, which is just the identity. And of course, now this is just the product of two separate inner products for each term in the sum. So we can rewrite it. By moving the first in front of the second. But now we just have a sum over the expectations in this orthonormal basis J of this operator ket psi I bra psi I times the projector PM, right? So that is just a trace. That's the definition of a trace. Sum over bra J operator ket J for some orthonormal basis J. This is just a trace. Psi I PM. And finally, everything is linear. So we can move this sum over I inside the trace to give us sum over I pi projector onto psi I, and then the whole thing just gets multiplied by PM. Okay, so this whole quantity in the brackets, the sum over I pi psi I, we call the density matrix of this ensemble, and it's conventionally labeled rho. Okay, so rho is just literally just defined to be a sum over I pi psi I. This is the density matrix.
Would the sum over I of ket psi I times bras psi I, would that also be the identity?
Yes, if you didn't have, well, not necessarily. That depends on whether the psi i's are an orthonormal basis. If these psi i's were an orthonormal basis and you didn't have the pi there, then that would indeed be the identity, right? But we could have the like psi 0 is just the 0 state on a qubit, and then psi 1 is the plus state, and ket 0 bra 0 plus ket plus bra plus is not equal to the identity.
Okay,
Thank
you. Yeah.
Awesome. No, very good question. Really appreciate all the questions. Okay, so if we want to know the probability of getting some measurement outcome M when we do some particular measurement where the projector is PM, then we don't actually need to know this whole sort of ensemble of states of all the PIs and the psi-i's. All we need to know is this one density matrix rho. And in fact, that's generally true. I mean, all the physical information about a state is all the observable information is just the measurement outcomes you get. So in fact, this density matrix rho encodes all the observable information about the ensemble pi psi I. Okay. And what by it's important to clarify here that this doesn't mean that rho can be used to determine the entire ensemble pi psi I. You can have very different ensembles that have the same density matrix rho. Just means that doing the probability distributions for doing different measurements on those different ensembles will always be the same if they have the same rho. So there's no no observable distinction between them. So just to give very explicit examples of some different ensembles that give the same same density matrix, right? We could have P of 0, P 0.5, and P of ket 1. 0.5, and that gives us rho is a half projector on a 0 and a half projector on a 1, so that's just a half times the identity matrix. And similarly, we could have P of sort of the plus state being 0.5, P of the minus state being 0.5, and then again we would find that rho is now it's a half plus 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 a half minus minus, and that's equal to a half times the identity. Okay, but this is not like something special to the fact that, you know, it's the identity. Yeah, we could also we could also have more complicated distributions where you have a quarter probability of being 0, a quarter of being 1, a quarter of being plus, a quarter of being minus. Again, density matrix is the same. In general, for any sort of non-trivial density matrix, there'll be infinitely many possible ensembles that all give the same density matrix. Okay. But, you know, in terms of the things we care about, which are the physical consequences of having a state, if the state, the physical measurement outcomes that we would observe, then all those ensembles give exactly the same outcomes. Okay, so now we've defined this idea of a density matrix rho, then let's look at some properties of it. Okay, so obviously it's it's a element. It's a matrix on the Hilbert space. So it's a map from the Hilbert space to itself, a linear map. It's also Hermitian. So if we have rho dagger, right, that equals sum over I, pi, psi I, dagger, which is obviously just sum over pi, psi I, which is just equal to rho. Okay, so the Hermitian conjugate of rho is equal to itself. Rho is a Hermitian matrix. In fact, it's slightly better, stronger than just being Hermitian. It's actually positive, semi-definite. So this just means, people who've forgotten this being defined in a linear algebra course, just means that all the eigenvalues are greater than or equal to 0, or equivalently, that if we have any state psi, then psi rho psi is greater than or equal to 0. So let's just see that that's true. So this is sum over I, pi, psi I, psi, sum over I, pi, modulus squared of psi with I, with psi. Okay, and that is obviously greater than or equal to 0 because all the pi's are greater than or equal to 0. And the final property of rho that we're going to care about is that it's trace 1. Okay, so let's just see that again explicitly. Well, the trace of rho is really just, there's a quick way to sum over I, pi, times the trace of psi I, which is just equal to bra psi ket psi. So that's just equal to 1 because the psi i's are normalized. It's the sum over I probabilities, sorry, which is of course probability all add up, not to 0 as I just stupidly wrote, they add up to 1. Okay. There's sort of a converse statement to this, which is for any positive semi-definite trace 1 matrix, we can find matrix rho, let's call that. We can find some ensemble pi psi I, whose density matrix is rho. Anyone have an idea for what the simplest way to do this might be? Any sort of trick for pulling out an efficient ensemble that gives rho?
Just look at the eigenvalues of the density matrix.
Awesome. So indeed, so in general, this is not going to be the unique ensemble. There's going to be infinitely many. But one way is to just use the eigenstate decomposition of rho. Right, so we can write rho as just a sum over the eigenvalues of the eigenvalue lambda I times the projector onto the normalized eigenstate I. Okay. Moreover, because rho is positive semi-definite, then these lambda i's are greater than or equal to 0, and the inner products of the states I are all normalized by construction. They're actually orthonormal in this case, so that's not terribly important. And the trace of rho equals 1, which means that the sum over I of the eigenvalues lambda I is equal to 1. Okay, so then it's very simple. We just say our pi's are going to be equal to the lambda i's, and our psi i's are just going to be equal to I. Okay, and then that ensemble will give us the density matrix rho. But I really want to emphasize that this is not the unique density matrix that, not the unique ensemble that has that density matrix. It's just an easy one to find if you want an example ensemble. Okay, so any questions about the basic definition of how what density matrices are and the properties they satisfy? Okay, awesome. We'll carry on. Okay, so now that we have this definition of a density matrix, we can actually just sort of redefine or maybe generalize the postulates of quantum mechanics to write them all in terms of density matrices. Okay, we're not going to be like defining new rules as such here. We're just going to be showing how the old rules can be reinterpreted or can be rewritten in terms of these new objects. Okay. So when we first introduced the postulates of quantum mechanics, we said that states are described by vectors in some Hilbert space. So now we're going to generalize that. We're going to allow these mixed states, and we're going to say that states are labeled instead by density matrices, which again just means rho greater than or equal to 0 and trace rho equal to 1, acting on some Hilbert space H. Okay, so this is just generalizing what we mean by a state to allow these sort of classical ensembles. It's not changing the rules, but it's sort of a nicer definition to work with in some ways. Postulate 2 was our measurement postulate. So previously, we said that a measurement was associated to a set of outcomes M, each of which had an associated projector PM. And we assumed that the sum, so we had PM squared equals PM dagger equals PM. It's Hermitian projector. And we had a sum over these projectors equal to the identity. Okay. And then, so previously, we said that the probability of getting measurement outcome M was just given by bra psi, PM, ket psi. Now we're going to say instead, say the probability of getting measurement outcome M, just going to given by the trace of rho times PM. Okay. So previously, after doing a measurement, the state became PM acting on the state divided by the square root of the probability of getting M for that state so that the size remain normalized. Right. So what does that mean? What happens to the density matrix? Well, this is what happens to each of the individual psi i's. They just obey the same. If the state was psi I, then the psi I just gets updated according to the rules we learned back in the second lecture. But we also need to think about how the probabilities get updated, right? Because by doing a measurement, you can learn something about which psi I you actually had in the first place. And the measurements just get updated according to Bayes' rule. So PI, your initial probability estimate of getting I goes to probability of getting M conditioned on I times PI divided by the probability PM. Okay, that's the new probability PI conditioned on getting the outcome M. It's just applying Bayes' rule. So what does this mean about what happens to rho? Well, it seems like it's going to be a bit complicated, right? So we have it's now a sum over our new PIs, which are PM conditioned on I times PI divided by PM. And then we have to update the psi i's. So ket psi I goes to PM acting on psi I divided by square root PM given I. And similarly, the bra psi I goes to PM psi I divided by the square root probability of M given I. But magically, now these P of M's given I's cancel out. And we find that this is just equal to sum over I, PI, PM, psi I, PM, all divided by PM. Okay, so we can just write this very nicely in terms of the density matrix. This is just take the density matrix, apply a projector, PM on either side of it. So you're projecting it to only act in the subspace supported by PM, and then just dividing through by the trace of rho times PM. Okay, so this is just effectively ensures that the trace of rho still equals 1. Okay. Okay, so so that's the rules for updating states if you have rho. As for ordinary quantum state psi, it turns out that if your m's are all integers, are all not integers, are all real numbers, then there's a particular simple rule for the expectation value of m. So the expectation value of m is just by definition the sum over m times the probability of finding m. So it's the sum over m times the trace of rho times PM. Again, we bring that inside the sum. So we bring the sum inside the trace. So this is just equal to what back in the second lecture I called the measurement operator O. Okay, this is the Hermitian operator whose eigenvalues and eigenvectors describe all the outcomes of the measurement. It's a very simple rule for finding the expectation value of M for some measurement. Okay. Okay. So then we have our final postulate of quantum mechanics, which we need to update. This one's going to be a simpler one than dealing with measurement operators. So this is just the time evolution postulate. Okay, so previously we had the time evolution at the state psi going to U times psi I for some unitary matrix U. What does that mean for rho? Well, it means rho goes to sum over I, pi, U acting on psi I, and then it's emission conjugate, which is U dagger to the right of bra psi I. And of course, this is just equal to U rho U dagger. Okay, so the density matrices evolve by conjugating them with U, which just means you take rho and you map it to U rho U dagger. Okay. Okay. Any questions on how those postulates all work in terms of the density matrix rho? Awesome. Everyone's very quiet today. Hopefully because this is a bit less technical stuff than Grover search. Maybe it's just because everyone's completely confused. But fingers crossed. Okay. So let me make one more comment, which is that if our density matrix rho has rank 1, then it has to have trace 1. So its eigenvalues have to add up to 1, but only one of the eigenvalues can be non-zero. That means that it just has to be equal to ket psi, bra psi for some normalized state, normalized eigenvector psi. Okay, so we call this a pure state as opposed to a mixed state. And that's because there is only one ensemble that gives this density matrix, and that is that the state is ket psi with probability 1. Okay. So these pure states, these rank 1 density matrices are the way we describe the ordinary quantum states with no classical probability involved that you guys have been used to. Okay. And one of the nice features, I seem to have switched thickness of pen. Oh, well, that's interesting. One of the nice features of working with the density matrix, even if the state is pure like this, is that previously it didn't matter if the state was psi or the state was e to the I phi times psi for some pure phase, some global phase e to the I phi, right? We treated those as the sort of same physical state. And it was sort of a redundancy of our description of the state by some vector psi that meant we sort of they seemed like they were distinct states, even though we actually treated them as the same physical state. Nice thing about using rho instead is that rho goes to e to the I phi times ket psi times bra psi times e to the minus I phi, right? Which is, of course, just equal to rho. So there's no redundancy of description for rho. And that's because it describes a vector, a projector onto the one-dimensional complex subspace spanned by psi rather than just the specific state psi itself. Okay, so it doesn't care about multiplying psi by something, which is definitely a nice feature. Okay. So what I now want to talk about just for a little while is the specific case of density matrices for a single qubit. Okay, so just as with ordinary quantum states of a single qubit, it turns out that because a single qubit is such a simple Hilbert space, then we can have a very nice geometrical picture of these density matrices, right? Okay. And the way we're going to do that is we're going to start by working in the eigenbasis for rho. Hilbert space is two-dimensional, so rho only has two eigenvectors. We're going to call the first one ket psi. Okay, and we're going to call the eigenvalue of ket psi p. Okay, if one of our eigenvectors is ket psi, then the other one just needs to be orthogonal to ket psi. And so the projector onto it can just be written as the identity minus ket psi. That way we can avoid talking about any other quantum state other than psi. And what's its eigenvalue going to be? Well, the trace has to be equal to 1. It means the eigenvalues have to add up to 1. So this is just going to be 1 minus p times the identity minus ket psi. Okay, so we can write this whole density matrix like a arbitrary density matrix is uniquely determined by a single probability p and a single state ket psi. And more than that, we can assume that p is at least 0.5. Okay, because if p is less than 0.5, then 1 minus p would be more than 0.5, and then we could instead work with the state orthogonal to psi. We call identity minus ket psi projector onto psi, the projector onto phi, and then we'd say that it's the state is 1 minus p times projector onto phi, and we call 1 minus pp. Okay, that clear to everyone? So yeah. So for example, let's say we have p equals 0.5, then rho, which is going to be a half, times projector on a psi, plus a half, times identity minus psi. And of course, this is exactly just a half times the identity. So if p equals 0.5, then rho is actually independent of the state psi. But if p is anything strictly larger than 0.5, then every different state ket psi gives a different density matrix rho. Okay. So this gives us a very nice geometric picture for these mixed states row. Which is just the mixed states are described by the interior of the block sphere. I'll explain what I mean by that more in just a sec. But recall back in lecture 3, I think, we noted that any state psi, after multiplying it by a global phase, you could always get it into the form cos theta over 2 times ket 0 plus e to the I phi times sine theta over 2 ket 1. Okay. And this was independent of phi if theta is equal to 0 or pi. And in general, we had 0 less than or equal to theta, less than or equal to pi, and we had 0 less than or equal to phi, so less than 2 pi. Okay, and so theta and phi parameterized a sphere. So we identified the set of states ket psi with the points on that sphere. Okay, now we're just going to add in one more thing, which is we have this probability P, and we're just going to call this P, which is between a half and 1, a half times 1 plus R, okay, where R is between 0 and 1, okay. And again, if P equals 0.5 and hence R equals 0, then the state is independent of both theta and phi. Okay, so this is just a parameterization of the unit ball, right? The interior of the unit sphere. So we have a very bad, very wobbly sphere here. And for example, we have a state now. Previously, we just had states sitting on the edge of the sphere, on the sphere itself. Now we can have states sitting in the interior. So for example, we can have the state sitting directly in the interior, right, at R equals 0. That corresponds to P equals a half, okay? And so this state, the single state at R equals 0 is just a half times the identity, okay? So as before, the state at the top was just the state ket 0, right? Or the density matrix, ket 0, bra 0. State at the bottom, ket 1, bra 1. What about the state sort of somewhere on this line between the top and the center of the ball? Well, that's just R equals a half and psi equals 0, 0. So if R equals a half, P is a half times 1.5, which is 3/4. So this is the state 3/4, probability of being 0, 0, and a quarter of being 1. Okay. And similarly, let's imagine state sort of, I don't know, let's make it almost out near the boundary over here. Right, we have R is pretty close to 1. And the theta is pi by 2, phi is pi. So this is maybe 9/10 times the minus plus like 1/10 plus plus. Okay. And I want to emphasize again that this doesn't mean the only way to make that density matrix is to have a 90% probability of having the state be minus and a 10% probability of having the state be plus. We could also, for example, have a 80% probability of it being minus and 1/10 probability of it being 0 and a 1/10 probability of it being 1. Okay, that's a different ensemble. It's a different probability distribution for the state, but it gives exactly the same density matrix when you add these up. And so it gives exactly the same physical observables. So there's no physical way to distinguish the two ensembles. Okay. This state right in the middle that was independent of psi has a special name because it's a kind of important state. It's called maximally mixed state. This generalizes beyond a qubit. Generalizes to multiple qubits. We say that it's maximally mixed if rho equals 1/2 to the little n times the identity. Basically means you have equal probability of having any state. There's no, we just have absolutely zero knowledge about the state. Okay. Any more questions about how density matrices tie in with the block sphere and how all that works? Cool. Okay, so yeah, at the moment, this all may seem slightly abstract and pointless because it seems like it only shows up if you have sort of a probability distribution over what the state might be. And here we go. We do have one question. If rho is independent of psi, it tells you something about the system in terms of information. Yeah, I mean, the point is that if p is equal to a half, then there's no preferred state at all, right? Like psi can be thought of here as like the most likely state for rho to be in. It's the pure state that rho is most similar to. It's like if you had to guess one particular pure state, then your best guess for what it is that rho is, your best guess would be the state psi, okay, because it has probability greater than half. But if the probability actually is equal to a half, then it's just as likely to be orthogonal to psi as it is to be psi. And in fact, it's also just as likely to be some linear superposition of psi and the state orthogonal to psi. Like you just have absolutely zero knowledge about the state whatsoever. There's no best guess at all because you just don't know anything. So hopefully that answers your question to some degree. But yeah, the thing I'm going to talk about for the rest of this lecture is what's called reduced density matrices. And the lesson is going to be that even if you just think you're talking about pure states, even if you think there's no sort of classical probabilities showing up, once you start trying to talk about the state of a subsystem rather than the state of the entire global system, then you inevitably find yourself talking about density matrices. Okay, so hopefully that will make more sense in a minute. Let's say we have some Hilbert space H, which is a tensor product of HA and HB. Okay. And we have some state could be pure, it could be mixed, but it's some global state. And we'll call the density matrix associated with this entire state just rho AB. Okay. And maybe like A is like something that we actually care about, you know, like a qubit or something like that, that we're interested in measuring and learning about the measurement outcomes for. Maybe B is something like incredibly huge, like maybe B is the entire rest of the universe. Okay, so it's this incredibly, incredibly large thing. So the sort of the amount of data, you know, the amount of information you need to describe this rho AB can be really, really, really huge. So it's just not practical to talk about the entire state of the system if you only actually care about the state of system A. Okay. So we want to describe state of just system A. Okay. And the reason we want to do this is we need to be able to describe the system we care about while being able to ignore the rest of the universe. If we couldn't talk about the state of a quantum system without also talking simultaneously about the state of Alpha Centauri, then we wouldn't be able to make much practical progress in physics. Okay. But sort of around lecture 3 and 4, I spent this huge amount of time emphasizing to you guys that with the ordinary formalism of pure state psi, then this just isn't generally possible. Right? Generally, sometimes you have a product state where you have psi is just a product of some psi A and some state psi B for system B. But sort of normally, in fact, generically, two systems are entangled and there's no way to talk about the state of system A on its own. Okay. Of course, when I said no way, I secretly meant no way without using density matrices. So what we want to be able to do is be able to predict outcomes of any measurement that's just on system A, right? Okay. So how does that measurement work? Well, probability of getting some outcome M is just a trace of some projector PM that acts only on system A, tensored with the identity on system B of rho AB. Okay, that's just the usual formalism for density matrices for doing measurements that we introduced earlier on in the lecture. But we can just write this out explicitly, write out the trace explicitly by expanding in some orthonormal basis for both A and for B. So we have I, J, projector, tensor the identity, rho AB ij. Okay, and summing over I and j, that gives us the trace. Because the basis for the tensor product is just given by all combinations of an orthonormal basis for A and an orthonormal basis for B. But now, what we can do is we note that this projector on A tensor the identity doesn't do anything at all to the state J, right? And so we can just sort of move it inside. Have a projector acting on I. Then we have what I'm going to call J, rho AB, J, which is just an operator on A, okay, where we've just like picked out the JJ matrix element. Have a sum over J here. And finally, we have an I again at the end. Okay. This in turn, just a sum over I, PMA, what I'm going to call rho A, I, where rho A, it's just this sum over A, J of rho AB, J. We have a special name for this, right? Just like a trace, this is independent of the particular orthonormal basis J that we use. And we call this a partial trace over subsystem B. Okay, so an ordinary trace, we just trace over the entire Hilbert space. It would take our operator acting on the entire Hilbert space and just convert it into a number. Okay, this time we're only doing a trace over the sort of B system. So it's converting our operator that acts on the whole tensor product of A and B into an operator that acts only on A. Okay, and so this in turn is just a trace of the projector times rho A. Okay, so this is just the usual formalism for doing measurements of the state of system A if the density matrix of A is rho A. Okay, so if we're only doing measurements on A, everything is encoded in this simple density matrix on A, rho A, that doesn't care at all about this giant system B that it was maybe entangled with. So rho A is called the reduced density matrix. It describes the outcome of any experiment that only involves system A. Okay. Let's see this in action, and we'll see something very, very interesting that happens that sort of explains why we needed to be talking about density matrices in order to be able to do this, in order to be able to restrict to system A without having problems. Let's suppose we have some state on A and B that is just going to be bind state is going to be the Bell state phi plus. Okay, in other words, the density matrix is just a projector on to phi plus. This is just some pure state, okay, but we're just describing it using the density matrix formalism. So we can expand this out. 1 over square root 2, 0, 0, plus 1 over square root 2, 1, 1, times the corresponding bra. Okay. Can write this out in full. It's a half. 0, 0, 0, 0, plus a half. 0, 0, 1, 1, plus a half. 1, 1, 0, 0, plus a half. 1, 1, 1, 1. Okay. So written out like this, it's not completely obvious that this is a pure state, but it really is because it's just a projector onto this bowl state. Okay. So it has one non-zero eigenvalue, which is phi plus. What about the reduced state? Well, rho A is defined as the partial trace over B, rho AB. So what is that? It's 0, rho AB, 0, plus 1, rho AB, 1. Okay, let's look at the terms in rho AB. Okay, so this adding a 0, a bra 0 and a ket 0 basically kills all the terms that don't have the system B be in a 0 state in the ket and the system B be a 0 state in the bra. Okay, so the only one that survives is this state here. And we're left with just an operator on rho A, which is just we have a 0 for A in the ket and a 0 for A in the bra. So it's just 0, 0. Okay. Have the second term. It's 1 rho AB 1. Again, the only term that survives from the full density matrix is this 1 over at the end, where both the bra and the ket are in the state for B are in the state 1. And in that case, A is in the state, in the ket is in the state 1, and in the bra is also in the state 1. So we find the reduced density matrix where A is a half 0, 0 plus a half 1, 1, which is just a half times the identity matrix. So even though our original state, rho AB, was pure, it didn't involve any classical probability distributions at all, then the state we've ended up with, the reduced state of the system A, is not just mixed, it's in fact maximally mixed. This is a general rule. In fact, we have some pure state on AB. Then we find that the reduced density matrix, rho A, is mixed if and only if the pure state was entangled. Right, so this is sort of unsurprising. If the original state, rho AB, equals sort of psi A, psi B, psi A, psi B, then when we partial trace over rho, we just get psi A. Psi A is still pure state. But if rho AB can't be written in that form, then we always find that the reduced state rho A ends up being mixed. So a nice thing about this formalism, well, one thing is it makes clear how important it is to be able to think about mixed states, because anytime you have the state being entangled between two subsystems and you throw one of them away, then the resulting state is mixed. Another nice thing it has is it allows us to start quantifying, at least to some degree, how entangled different states are based on the density matrix that you end up with. And in particular, all the Bell states are what's called maximally entangled. Because the reduced states, rho A, are maximally mixed. So maximally entangled means that even though you have complete information, you know exactly what the sort of global state is, you know exactly that it's say phi plus, it can't be anything else, no probability of being anything else, then you have absolutely no information at all about the state on just A. Okay, for as far as like the state on just A is like completely undefined. There's completely no information about it. Okay. So I've got a bit of time left. I was sort of planning to leave it here, but I do have a bit more time. So I think I'm going to briefly cover what's called the Schmidt decomposition. Okay, so let's say I have some state psi in HA tensor HB, is in general entangled. Okay. We always can look at the reduced state, rho A, just a trace of a B of psi psi. And this will be some matrix. And in particular, it's a matrix that always has a eigenvalue decomposition. Okay, so we can always write this as sum over I, lambda I, psi I, psi I. More than that, we have that the lambda i's greater than or equal to 0, and sum over lambda I is equal to 1. This just comes from the fact that rho A is positive semi-definite and trace 1. Okay. You can check, by the way, that that's still true when you look at reduced density matrix. It's a pretty simple exercise to check. I encourage you to do it. I might put it on the homework. Okay. So now, what can we do? We can use this basis, psi I, for A, and use it to expand our original state psi. So, in other words, we can write the full state psi as just a sum over I, some coefficient Ci, psi I, let's call this phi I. Okay, so this is just, we could do this for any basis for A that we want, right? For any state in the tensor product, you can always just expand it in terms of an orthonormal basis for the first system A, and then some states, just whatever you end up with for system B, okay? But at the moment, so these are normalized because we can choose CI, so that the states phi I are normalized. But if for some general basis for A, there's no guarantee for these different states, psi I equal to 0. Okay, so for example, we might have the state psi is plus state times the 0 state. If we expand that in the computational, expand A in the computational basis, then that's 1 over square root 2, 0, 0, plus 1 over square root 2, 1, 0, right? So in this case, the states phi I for B would both be equal to 0. And the CIs would be 1 over square root 2. Okay. So that's all just using the fact that the psi I is an orthonormal basis for A. We haven't yet used the fact that the reduced density matrix rho A is lambda I, psi I, psi I. So let's now do that. We know trace over B, ket psi, bra psi, equals. Okay, so what is this? Sum of I j, ci, psi I, psi j, cj star times the trace of psi I, psi j. Okay, we just used the linearity of the trace to separately do it for, we expanded both the ket psi and the bra psi in terms of these product states. And then we could just take the A's part out the front because our partial trace over B doesn't do anything to them. And so, let me make clear that this is a separate thing. This in turn, this trace over psi I, psi j is just the inner product of I and j. So this is sum over I and j, ci, cj star, psi I, psi j, times inner product of phi I with phi j. Okay. But this, the trace over B of psi I, psi I, sorry, of psi, ket psi, bra psi, we know is equal to just a sum over I of lambda I, ket psi, bra psi. Okay, and the psi i's by construction, because of the eigenbasis of rho A, form an orthonormal basis. Hence, comparing terms, right, on the left-hand side, we have no terms that look like psi I, psi j, where I is not equal to j. So we find that phi j, phi I is equal to 0 when I is not equal to j, just by comparing terms on the two sides. So the psi i's form an orthonormal basis. This would not generally be true if we expanded A in some arbitrary basis, as we saw, but it is true when we expand it in the eigenbasis of the reduced density matrix. And we also have modulus ci squared is equal to lambda I. Okay, which in turn, yeah, I call this lambda I. I'm going to switch to calling it pi because that's what it is. It's a probability. That's up to 1. Plug all that into our original state psi. We find that psi is equal to a sum over I. Also, we can choose our states phi I and psi I so that the CIs are real, right? We can absorb any phase that CI has into either psi I or phi I. So we can make them CI real and positive. So we just have a square root of pi times psi I times phi I, where psi I psi j equals phi I phi j equals delta ij. So both bases are orthonormal, and sum over I pi is equal to 1. Okay, so this is called the Schmidt decomposition. Psi. The nice thing about it is that, you know, if we just work in the psi I basis and the phi I basis, yeah, so if we generically expanded in some orthonormal bases, I and j, we would have psi be a sum over I and j of some amplitude Cij I times j, have d squared terms, right, where modulus of the Hilbert space, we would have dA times dB terms, where the dimension of the Hilbert space A is dA, and dimension of Hilbert space B is dB. Okay. By using these particularly nice orthonormal, particular orthonormal bases, psi I and phi I, only have the smaller. The number of terms is only the smaller of those two dimensions, right? Because we can only have at most dB different phi I's and at most dA different psi I's. Okay, so this is a much more efficient representation of the entangled state. It's roughly, it's very closely analogous to the representing a matrix in its eigenbasis rather than in an arbitrary basis, right? In an arbitrary basis, it has d squared different elements. In its eigenbasis, then we only need to know the d eigenvalues. It's a much more efficient representation in that sense. Of course, you still need to know what the eigenvectors are, and so you still need just some data, but the eigenvalues are far more efficient, pure amplitudes. Okay. Yeah, so that stuff at the end about Schmidt decompositions was just, we had a bit of extra time, so don't worry too much about it. The main takeaway from this lecture should be just how densities matrices work, and in particular, this very important point that even if we start with a pure state, we don't have any classical probabilities for our sort of entire system. When we look at subsystems, if those subsystems are entangled with one another, then you naturally end up talking about mixed states. Okay, any questions on the last parts of that? Okay.
Uh,
Awesome. Thanks. Oh yeah, go ahead.
If I have like say I'm doing some experiment and I have like a density matrix for my system, can I
Yep.
assume that it's like it's been like traced over the universe and what I have is
Yep.
like the row AB?
Yeah, exactly. So in some sense, always the right way to think of it is anytime you have some quantum system and you want to think about its state, then it will be entangled with the universe. Like you can always think of the density matrix as just coming for some pure state, but then we've traced over the rest of the universe and we've ended up with a mixed state. Yeah, that's absolutely the way to think about it.
Okay, thank you.
Cool. Any other questions?
I think I have a question.
Yep.
In our last description of quantum mechanics, it seems like it was not complete. And with this density matrix, we have the most complete description of quantum mechanics. Or
What do you mean by not complete?
I mean that you have situations that you cannot describe with a wave function, for example, when you have ensembles.
Yeah, so yeah, and in particular the fact that with the pure state formalism, then you can't talk about the state of a subsystem at all. That's kind of a major problem. And yeah, being able to talk about density matrices is like density matrices really are the right way to talk about quantum mechanics, even though it seems like ad hoc you're adding in these classical probabilities because looking at subsystems, you naturally end up with density matrices. They just are the right framework to think about things. Yeah. So I guess I would agree with the spirit of what you're saying there. Yeah. Does that answer your question, or have I misinterpreted?
Yeah. Yes. Thank you.
Okay. Awesome. Okay. Thanks very much, all. See you guys on Tuesday.
Thank you.